Have you ever stared up at the night sky and wondered if we could ever reach the stars beyond our solar system? For decades, scientists, dreamers, and science fiction writers have imagined a way to skip the long, slow journey across the cosmos, a shortcut that bends space and time itself. That shortcut is a wormhole, a hypothetical tunnel in the fabric of space-time that could connect two distant points in the universe in an instant. Today, we're going to explore the real science behind wormholes, ask if they can truly make interstellar travel possible, and journey through the mind-bending physics that makes these cosmic tunnels one of the most fascinating ideas in all of astrophysics. This is not just science fiction. This is the cutting edge of what we know about the universe we call home. To understand wormholes, we have to start at the beginning. Albert Einstein's General Theory of Relativity, published in 1915. Before Einstein, we thought of gravity as a simple force pulling objects together. But Einstein changed everything. He showed that gravity is not just a force, it is the curvature of space-time caused by mass and energy. Imagine space-time as a giant, stretchy sheet. When you place a heavy object like the sun on that sheet, it warps the fabric around it. Planets don't orbit the sun because some invisible string pulls them. They follow the curve of space-time created by the sun's mass. This revolutionary idea explained everything from the orbit of Mercury to the bending of light around stars, and it earned Einstein a permanent place in the history of science. But buried within the complex math of general relativity was a strange, unexpected prediction, a bridge connecting two separate points in space-time. In 1935, Einstein and his colleague Nathan Rosen published a paper that described this bridge mathematically. They called it an Einstein-Rosen bridge, but today we know it by a simpler, more evocative name, a wormhole. Think of the universe as the surface of an apple. If an ant wants to go from one side of the apple to the other, it can crawl all the way around the skin, a long, slow trip. But if the ant burrows a hole straight through the apple, it reaches its destination in a fraction of the time. That hole through the apple is a wormhole for the ant, and a wormhole in space-time is the same idea for a spaceship. It doesn't just speed up travel. It rewrites the rules of distance entirely. A wormhole could connect our solar system to a star 10,000 light-years away, letting us cross that gap in hours or days, instead of the tens of thousands of years it would take, with even the fastest rockets we can imagine. At first glance, this sounds like the perfect solution to interstellar travel. The universe is incomprehensibly large. The nearest star to Earth, Proxima Centauri, is 4.2 light-years away. Even if we built a spaceship that could travel at 10% the speed of light, a speed far beyond any technology we have today, it would take 42 years to reach it. A galaxy, like the Andromeda Galaxy, is 2.5 million light-years away. Without wormholes, human exploration of distant galaxies is impossible. Even the speed of light is too slow to bridge those cosmic gaps. Wormholes offer a way out, a loophole in the universe's speed limits. But here, as the catch, Einstein and Rosen's original wormhole was not a stable tunnel. It was a temporary structure that would collapse in an instant, long before anything, not even light, could pass through it. The math was clear. The natural wormhole predicted by general relativity is a dead end. It forms and closes so quickly that it is completely useless for travel. So why do scientists still talk about wormholes? Because, in the 1960s and 1970s, physicists began to ask a critical question: could we stabilize a wormhole? What if we could hold the tunnel open, stop it from collapsing, and turn it into a usable passage through space-time? The answer came from a strange and exotic concept: negative energy. To keep a wormhole open, we need a form of matter or energy that pushes outward on the walls of the tunnel, counteracting the immense gravitational force that tries to squeeze it shut. This material is called exotic matter, and it's nothing like anything we've ever found on Earth. Exotic matter has negative mass, or negative energy density, a property that defies our everyday understanding of physics. Normal matter pulls things together with gravity. Exotic matter pushes them apart. It is the cosmic glue that could make wormholes travelable. Now, you might be wondering, does exotic matter actually exist? So far, we have never found or created stable exotic matter in a lab. But we have observed a hint of negative energy in a quantum physics effect called the Casimir effect. In this experiment, two metal plates are placed extremely close together in a vacuum. The space between the plates has less energy than the empty space outside them, creating a tiny region of negative energy. This is a real, measurable effect. And it proves that negative energy is not just a fantasy. It exists in the quantum world, even if we can't yet scale it up to the size needed for a wormhole. For physicists, this is a crucial clue. It means the basic building blocks of a stable wormhole are not impossible. They re just beyond our current technological reach. NASA has been paying close attention to this research. In recent years, scientists at NASA's Jet Propulsion Laboratory and other space agencies have published papers exploring the mathematical feasibility of wormholes. They've run computer simulations to model how a stable wormhole would look, how it would bend light, and what kind of exotic matter would be needed to keep it open. These studies are not science fiction. They re-serious theoretical physics. NASA's researchers have even calculated the size of a wormhole that could safely carry a human crew, a tunnel about 100 meters wide, held open by a shell of exotic matter that balances the gravitational forces inside. The simulations show that a spaceship passing through such a wormhole would not experience extreme gravity or time dilation. It would be a smooth, relatively gentle journey. Of course, this is all theoretical. We can't build a wormhole today, but we're getting closer to understanding the rules that would let us do it someday. One of the biggest misconceptions about wormholes is that they're just a tool for fast space travel. But wormholes could do far more than connect 2 points in space. They could connect 2 points in time. Because space-time is a single fabric bending space, also bends time, a wormhole could, in theory, act as a time machine, letting travelers move forward or backward in time, as well as across the universe. This idea raises all the classic time travel paradoxes. What if you went back in time and changed the past? Would it erase your own existence? These paradoxes have puzzled physicists for decades, and they add another layer of mystery to wormholes. But even if we ignore the time travel aspect, the possibility of interstellar travel alone makes wormholes one of the most important topics in modern astrophysics. We also have to consider where wormholes might form naturally. Could there be wormholes floating in space right now, waiting for us to find them? Some physicists believe that tiny wormholes may have formed in the first moments after the Big Bang, when the universe was infinitely dense and space-time was twisted into extreme shapes. These primordial wormholes could have been stretched to enormous sizes as the universe expanded, and some might still exist today. But finding a natural wormhole would be incredibly hard. Wormholes don't emit light or radiation, and they would be hidden among the countless stars and galaxies in the sky. We wouldn't see the wormhole itself. We'd see the light from distant stars bending around it, a signature similar to a black hole, but with unique differences. The James Webb Space Telescope, the most powerful space telescope ever built, is scanning the cosmos for these exact signatures. It is possible that Webb could give us the first real evidence of natural wormholes in our lifetime. Let us compare wormholes to the other big idea for interstellar travel: warp drive. Made famous by Star Trek, warp drive works by bending space-time around a spaceship, shrinking the distance in front of the ship, and stretching the distance behind it. Like wormholes, warp drive relies on exotic matter to work, and it's still purely theoretical. But wormholes and warp drive are very different. A warp drive moves the ship through space. A wormhole moves space itself, carrying the ship along for the ride. Wormholes are also more stable in mathematical models. Warp drive requires an enormous amount of energy and creates dangerous space-time distortions that could destroy the ship. For now, wormholes remain the more promising of the two ideas for real interstellar travel. So, when will we be able to build a wormhole? The honest answer is, we don't know. It could be 100 years, 1,000 years, or never. We face three huge challenges. First, we need to find or create large amounts of stable exotic matter, something we have no idea how to do right now. Second, we need to master the ability to manipulate space-time itself, a skill that would require technology far beyond anything we have today. Third, we need to solve the safety problems. Would a wormhole damage a spaceship or its crew? Would the journey be survivable? These are not small hurdles, but they're not impossible either. Every day, physicists make new discoveries about quantum mechanics, gravity, and the nature of space-time. Every breakthrough brings us a little closer to turning the wormhole from a mathematical equation into a real machine. The universe is full of mysteries that once seemed impossible to solve. 100 years ago, we didn't know that other galaxies existed. 50 years ago, we hadn't walked on the moon. Today, we're sending rovers to Mars and telescopes to study exoplanets that might harbor life. Wormholes are just the next frontier. They represent humanity's endless desire to explore, to push beyond the limits of our world, and to reach for the stars. Even if we never build a wormhole, studying them teaches us more about the fundamental laws of the universe. It forces us to rethink what we know about space, time, and reality itself. Wormholes are more than just a way to travel. They reveal a window into the deepest secrets of the cosmos. As we wrap up this journey through the science of wormholes, let us take a moment to look up at the stars again. Those tiny points of light are not just distant suns, they read destinations. And wormholes, the cosmic shortcuts that bend space-time itself, might be the key to reaching them. We may not have all the answers today, but we re-asking the right questions. We re-exploring the edges of physics, pushing the boundaries of human knowledge, and dreaming of a future where interstellar travel is not just a dream, but a reality. The universe is vast, beautiful, and full of surprises. And somewhere, in that vastness, wormholes might be waiting for us to find them. Please like, comment, share, and subscribe to the channel.